Hello, I am Jagadeesha, Assistant Professor of Physics, Government College Autonomous Mandya. In this video lecture, I will explain dielectrics, types of dielectric materials, classification of dielectric materials, and the dielectric polarization. As we know, materials are of three types: conductors, insulators, and semiconductors. Conductors are the materials have large number of free electrons. Insulators are the materials having large number of bound electrons. That is, no free electrons are available for conduction. Whereas semiconductors are the materials which are lies between conductors and insulators. That is, the semiconductors behaves both as conductors and insulators. At high temperature, semiconductors behaves like a conductors, and at low temperature, semiconductor behaves like a insulators. Here, dielectrics are purely insulators. They do not conduct electricity because they have no free electrons. Therefore, dielectrics will have high resistivity and very low conductivity. And also dielectrics will have large energy gap around 3 eV or more than 3 eV. That is, there is a large energy gap between valence band and the conduction band compared to conductors and semiconductors. Study of dielectric properties is concerned with the storage and the dissipation of electric and magnetic energy. Types of dielectric materials. There are three types of dielectric materials: solid dielectrics, liquid dielectrics, and gas dielectrics. Porcelain, glass, rubber, mica. These are all some of the solid dielectrics which are used in all kind of electrical circuits for electrical insulation. Transformer oil, cable oil, silicon liquids are liquid dielectrics which are used as insulating liquid for electrical insulation and to dissipate heat. Here, hydrogen, nitrogen, helium, propane, etc. are gaseous dielectric which are used as an insulator and as cooling agents in high voltage applications, particularly in a transformer. Dielectrics are used for insulation for wires, cables, and many electrical equipments. And also they are used as polarizable media for capacitors to store electrical energy. In the market, there are plenty of capacitors are available in which paper, mica, and oil-filled capacitors are used to store electric charges and electrical energy. Dielectrics are also used for the propagation or reflection of electromagnetic waves, and in many semiconductor devices, piezoelectric transducers, dielectric amplifiers, and many elements, memory elements in computers. We know that every atom consists of a positively charged core called nucleus. Around the nucleus in different circular orbits, negatively charged particles called electrons or revolves. When this atom is kept in electric field, this electric field is set up in between the two plates X and Y, which is connected to battery. The center of positive charge and center of negative charge of the atom separates due to the application of electric force on the atom. So these equal and opposite charges separated by a distance x. So dipole moment is set up. This dipole moment is a measurement of separation of two equal and opposite electric charges. The displacement of the charge depends on the strength of the electric field applied in between the two plates X and Y. Classification of dielectrics. Based on the dipole moment, dielectrics are of two types: polar dielectrics and non-polar dielectrics. Polar dielectrics made up of polar molecules and non-polar dielectrics made up of non-polar molecules. The next question is, what are polar molecules? Polar molecules have permanent electric dipole moment. For example, HCl, H2O, N2O, etc. These molecules will have permanent electric dipole moment. That is, The center of positive charge and center of negative charge do not coincide. Here I take two examples. One is HCl and another is H2O. These molecules will have permanent electric dipole moments. In the absence of the electric field, all the electric dipoles orients in a random manner in all possible directions. If the polar molecule is kept in electric field, the dipole aligns or orients along the direction of external field, external electric field. In the absence of the external electric field, the average moment per unit volume is zero. But in the presence of the electric field, the average average dipole moment can never be zero. So this is the electric dipole moment between O and H. This is the electric dipole moment between O and H. So this P is the resultant of P1 and P2. In the absence of the electric field, the electric dipoles orients in all possible directions. In the presence of the electric field, the dipoles aligns parallel to the direction of applied electric field. This alignment is increases if the strength of the applied electric field also increases. The next one is nonpolar molecules. Nonpolar molecules do not have any permanent electric dipole moment. For example, CO2, CCl4, oxygen, nitrogen, etc. Here I take the example carbon dioxide, in which the dielectric dipole moment between first oxygen atom and carbon atom is P1. The electric dipole moment between second oxygen atom and the carbon atom is P2. These two dipole moments are equal and opposite, therefore the net dipole moment is zero. If the same carbon dioxide molecule is kept in the external electric field, the electric dipole moment between the first oxygen atom and the carbon atom is P1, and the electric dipole moment between the second oxygen atom and the first carbon atom is P2. So the resultant dipole moment is the difference of the dipole moments of first oxygen atom to carbon and second oxygen atom to carbon. If the electric field is applied perpendicular to the line joining the atoms, the resultant electric field is the sum of the electric dipole moments developed between oxygen and carbon and this oxygen and carbon. Here the main difference is, here the electric field is applied parallel to the line joining the atoms. Here the electric field is applied perpendicular to the line joining the atoms. So the direction of the induced dipole moment is along the direction of external electric field. The next is dielectric polarization. I have already told when an atom is kept in an electric field, the center of positive charge and center of negative charge separates. Therefore, dipole moment is created. In the absence of the electric field, the dipoles are orients in all possible directions. But in the presence of the electric field, the electric dipoles aligns or orients parallel to the direction of applied electric field. Therefore, an electric field is set up inside the dielectric. This electric field is called induced electric field. This induced electric field is opposite to the direction of applied electric field. This induced electric field try to decrease the strength of the applied electric field. So if the strength of the applied electric field increases, the polarizability of the dielectric material is also increases. So the alignment of the electric dipole moments of the permanent or induced dipole, which the direction of applied electric field is called dielectric polarization. The strength of the dielectric polarization increases when the applied electric field strength is also increases. Here, E naught is the strength of the applied electric field. EP is the electric field induced inside the dielectric. This induced electric field is opposite to the applied electric field. Totally, this induced electric field decreases the strength of the applied electric field. Therefore, the strength of the polarization increases if we increase the applied electric field strength. How do we increase the applied electric field strength? If we increase the voltage across the battery, the applied electric field strength also increases. If the applied electric field strength increases, the resultant electric field E is also increases. If the resultant electric field E increases, the polarization extent is also increases. Therefore, polarization is directly proportional to the resultant electric field E in the dielectric, inside the dielectric. So P is proportional to, E. So P is equal to alpha into E, where alpha is called atomic polarizability of the dielectric. This can also be written as P is equal to epsilon into chi E into E, where chi E is the electrical susceptibility of the dielectric. The next question is, what is electrical susceptibility of the dielectric? The degree of polarization of a dielectric material in response to an applied electric field. Actually, electrical susceptibility measures how easily it polarizes in a response to an electric field. I mean, if the dielectric medium is kept in between the plates of the capacitor, the extent of polarization depends on the strength of the electric field. So the electric susceptibility can be measured by knowing the relative permittivity of the dielectric. Here in the table, different materials will have different dielectric constant. If you knowing the dielectric constant, we can easily find out the electrical susceptibility of different dielectric materials. Here, one point to be noted here, the electrical susceptibility is the measure of degree of polarization of the dielectric material when it is kept in electric field. So the greater the electrical susceptibility, greater the ability of a material to polarize. Here, E naught is the strength of the applied electric field, which is applied in between the plates X and Y. And EP is the electric field setup or induced inside the electric. So induced electric field is opposite to the applied electric field. So the resultant electric field E is equal to E naught minus EP. So the charge induced on the surface of the electric field is called bound charge. These are the bound charges induced on the surface of the dielectric. So P is equal to QB divided by A. So this is called surface charge density due to polarization. And also displacement vector is equal to free charge per unit area. Free charge means the charge on the plates of the capacitor. The charge on the plates of the capacitor is nothing but free charge. So the displacement vectors can also be written as Q divided by A. Q is nothing but the amount of charge presenting on the plates of the capacitor. This is equal to surface charge density on the plates of the capacitor. As we know the relations according to Gauss theorem, E naught is equal to sigma by epsilon naught, EP is equal to sigma P by epsilon naught. Substitute these equation 4 and 5 in equation 1, we get this equation. So after the simplification, we get D is equal to epsilon naught E plus E plus P. But the polarization is equal to epsilon naught chi E into A. Here epsilon naught is the absolute permittivity of free space. Chi E is the electric susceptibility. E is the resultant electric field. When I substitute here, we get the final equation D is equal to epsilon naught A. This is the relation between electric displacement vector and the resultant electric field. Here epsilon naught is the absolute permittivity of free space and its value is 8.85 for 10 to the power of minus 12 farad per meter. Epsilon r is the dielectric constant or relative permittivity. This is different for different materials, different electric materials. Okay, thank you.